Hello and welcome to Chapter 11. Chapter 11 we'll be going over inference about a mean. In this chapter we're going to learn about the estimated standard error of the mean, something we've already done. We're going to change it up a little bit. And we're going to go and talk about students' t distribution, a one sample t-test, the confidence interval for mu. We're going to then talk about paired samples and the conditions for inference, along with sample size and power, which everyone loves to do. We'll be going over it, but rest assured we're not going to be tested on this part. There's plenty of other things to know as opposed to kind of the nitty-gritty for sample size and power. So without further ado, let's start talking about the estimated standard error of the mean. We've done this before with in the previous chapters, and to be frank, a lot of times we rarely know the population standard deviation as sigma. We calculate the sample standard deviation S and use this as an estimate of the standard deviation, or sigma. Remember, when we start talking about the difference between our sigma versus our standard deviation, it really comes down to the formula and whether or not we're using the degrees of freedom of n-1 when we're calculating from our sample. So moving forward, when we're talking about the estimated standard error of the mean, we're not going to be giving a known standard deviation of the population, so we're going to have to use the standard deviation of the sample size. So our standard error of x is going to change. Instead of being sigma over the square root of n, it's going to change to s over the square root of n. Using s instead of the sigma adds a source of uncertainty. As z procedures no longer apply, use t procedures instead. Right, if we don't know the population standard deviation, which most of the time we probably won't, then we have to revert back to using the standard deviation that we learned about earlier in the year. Moving on to 11.2, student t's distribution. So it's a family of distributions identified by a student. His name was actually William Gosset in 1908. He went under the pseudonym of Student. And he's the one who kind of discovered this. He used the T family members are identified by their degrees of freedom, notated by DF, degrees of freedom, which, as we learned a couple weeks ago, it's the number of independent variables that can vary, that are free to vary. T distributions are similar to Z distributions, but with broader tails. You'll see this in a second. And as the degrees of freedoms increase, the t-tails get skinnier and t becomes more like z. So as the number of study samples you have, whether that be people or whatever you're looking at, increases, the t distribution becomes very similar to a z distribution. As you can see here, you have the t probability density functions with 1, 9, and infinity. So here's your infinity, and it looks very similar to our normal kind of bell-shaped curve. As the degrees of freedom decrease, though, as they decrease, imagine kind of squishing down from the top and pushing down. You can see that the apex, the top part of our distribution, gets squished down, and so the tails get fatter at the end. So as you push it down, the tails get fatter at the end, and as your degrees of freedoms increase, the tails get broader and become more similar to a z distribution. And so because we have a whole new procedure with our t procedures, we have a whole new table. Instead of using the z table, now we're going to the t table, which is table C in the back of the book. You'll find this right next to our b table in the appendix. It's on page 545. And it's a pretty cool table, so cool that they printed it sideways instead of straight up and down. And you'll notice that it's laid out a little differently, but very similar. So you'll look up the t-values, and the t-values correspond to the probabilities. So our entries are the t-values, the rows are the degrees of freedoms, and the columns are the probabilities. So you'll see the degree of the freedoms on the left-hand side, and on the first page you'll see degrees of freedom 1, 2, 3, 4, 5, and when you flip over, it goes all the way to 30, and then it starts jumping up by 20, 10, 20, every time, all the way up to 1,000, And then you'll see at the very top, you'll see cumulative probability, upper tail probabilities, and probabilities in two tails. This all kind of goes back to depending on what side of the I'm losing my train of thought. What side of the distribution you're on, right? How your hypothesis statement is set up, whether your alternative hypothesis is looking at a greater than, a less than value, or not equal to value. That's where we'll determine whether you'll be looking at upper tail probability or probability in two tails and the value associated with them. So an example of this is you had a t-value with degrees of freedom and the cumulative probability. So it was always notated as t degrees of freedom and the cumulative probability. So if you had an example of t9, 0.90, you'll know that the t9 is the degrees of freedom and 0.90 is the cumulative probability. So when you look that up, if you go to the table, you'll find your degrees of freedom 9, go and find your cumulative probability, where you'll find 0.90, and then where those meet is where you will find your t-value of 1.383. And that is how you use the table. Notice, though, that you won't, the table doesn't have all the values, just like Z didn't have all the values, so same rules as before apply. We'll be doing, the same rules as we did for the Z table, and you'll have to, we're not going to guess, but we're going to use our best logic going forward when we're trying to figure out, what is our p-value going forward. So the 10th and 90th percentiles on a T9, from this one was 0.90. So you'll have your left tail being shown here and your right tail seen here. You'll notice that because it's symmetrical, each side is the same number, right? The scale is symmetrical, so a lot of times, depending on what you're looking at, you could use absolute values, which is what we will be using, especially if we have a negative t-value number. We're going to have to use absolute values in order to come back to the table and find the probability associated with it, and then take that into consideration when we're using absolute values, depending on what side of the distribution we're on. Okay, so now we're going to do a one-sample t-test just to go through it. So on our one-sample t-test here, we have our null hypothesis, an alternative hypothesis. Remember, if you're using less than its left side and greater than its right-sided, you're going to then use your t-test statistic, which is going to be your t-stat here, and it's going to equal your x-bar minus your mu naught, or mu of 0, divided by our new standard error equation, right, which is going to be our standard deviation, denoted as S, divided by the square root of n. And then you will calculate your degrees of freedom as n minus 1. Then we'll find the t-stat converted to a p-value using Table C or other software. You can use Excel, but for the purposes of us, we'll be using the table. Remember, strong p-value, stronger evidence against the null hypothesis. And then we also have our significance level, which you can write as an optional. Remember, that's when we go in Chapter 9, where depending on if it's greater than 0.10, if it's between 0.05 and 0.1, or between 0.05 and 0.01, or less than 0.01, we have whether it's not significant, marginally, highly, statistically significant, all those. So you have one sample t-test. This we have to state the problem. So do SIDS babies have lower than average birth weights? We know from prior research that the mean birth weight of the non-SIDS babies in this population is 3,300 grams. We study N equaling 10 SIDS babies to determine their birth weights and calculate X bar equaling 2890.5 and a standard deviation of 720. So do these data provide significant evidence that SIDS babies have different birth weights than the rest of the population? Right, so when we're doing a t-test, we're looking at two different independent groups and seeing if they are significant against each other. So here we have a one sample t-test. where we have our null hypothesis, where mu is going to equal 3,300, versus alternative hypothesis, where mu is not going to equal 3,300, right? Because we don't know whether the birth weights are going to be higher or lower. We're just comparing to see if there's an actual difference between the two. So we're going to use a two-sided hypothesis test. So we're going to use our test statistic here, where we have our t-stat is equaling x bar minus mu naught, which our x bar for our group was 2890.5 minus 3,300, divided by 720 as the standard deviation, divided by the square root of 10, which equals negative 1.80. Calculated degrees of freedom. Remember, our degrees of freedom is calculated as n minus 1, so 10 minus 1 is going to equal our 9 degrees of freedom. Our p-value associated with this is going to be 0.1054, which is very weak evidence against the null hypothesis, and our data is not significant even at an alpha level of 0.10, right, because this is greater than 0.10. And also just to clarify, 0.10 is not one that we often use a lot in research. We normally want it at even an alpha level 0.05 most of the time or less. So converting the t-stat to a p-value. So p-value via table C wedge. So we're taking the absolute value of the t-stat. So our t-stat here was negative 1.80. So negative 1.80. When we're using the absolute value of it, it then becomes just 1.80. Okay, so it's wedged the absolute value t-stat between the critical value landmarks on the C table. So one-sided tail would be 0.05 greater than p, which is less than 0.10, and two-tailed test shown here. Our table C is a traditional table. As you'll see here, the absolute value t-stat of 1.80 will fall in between this wedge here, right? And it's closer, it's under 1.83, but greater than 1.308. And so we'd have to really kind of look at the degrees of freedom 9. Remember, you have to go down 10 minus 1 degrees of freedom, then go over and find on degrees of freedom 9 where this value of 1.80 falls in between. And as you can see, within the cumulative probability and upper tail probability is where it determines. But remember, this is just if you use upper tail probability at 0.05, right? Because that's kind of what we're looking at. It's going to be very similar to that because it's 1.80 is very close to 1.83. So it's going to be a little over 0.05 value, and then we're going to multiply by 2 because we're doing the alternative hypothesis of not equal to, so multiply the p-value times 2 to truly get there. One way that definitely makes it a little easier is using the p-value via software, but as you can see, you can kind of really put it, it's going to be between the 0.10 and 0.05 on our C table here, and we know it's going to be closer to 0.05, but when we double it for our alternative hypothesis, it's, you know, even at 0.05, doubling that is not going to get us anywhere significant. And here is a visual representation of the two-tailed p-value SIDS illustration that we just did. So the actual p-value would be 0.0527. We multiply that by 2, and that's where we get our 0.1054. And as you can see, this is where they fall. And so we can say that we can determine that the SIDS babies versus the other babies in birth weight, that their birth weight doesn't significantly differ from one another. The next part, it goes into confidence intervals, but I'm going to stop this video here and pick up the next one in just a bit.